Okay, so the final speaker in this session is Davide Trotta, who's going to talk about Sheafification as a geometric tripos-to-topos adjunction.
Thank you very much. I'm very glad to present this joint work with Billy Maglietti, where the main goal of this talk, as you can imagine from the title, is to show how we can use the tripos-to-topos construction to generalize, to abstract and generalize the ordinary Sheafification that we have in the locality case. So the main goal is to generalize this Sheafification and then to explain how we can use this construction to generalize some properties which are, some features which are typical for example, of locality toposes or locality triposes to other triposes and toposes. So, before starting with all the details, I would like to make a very short summary with a little bit of history of about the tripos-to-topos construction, explaining I want to explain what are our motivations and what is the main result that I want to present today. So, the tripos-to-topos is a construction that was originally introduced by Martin Island, Johnston and Bizzi in this paper, and it is essentially a generalization of Higgs presentation of the sheaf construction for a given locale to a particular kind of Liouville hyperdoctrines called tripos. And well, the idea is that this is a construction that takes a tripos, which is a particular functor, we will see all the detail later, and produces a topos. As I said, this is a generalization of the ordinary construction of the topos of sheaves for a given locale, because when we apply this construction to this functor where this is a locale, so the locality tripos, we obtain precisely the ordinary locality topos. And well, the idea is that we know that, for example, in the case of localic toposes, well, there is we can also define, for example, another category starting from a locale. That is the category of presheaves. And we have an adjunction here, which is the ordinary, the well-known Sheafification. And, well, the main purpose of our work is to explain how we can use the tripos-to-topos construction to abstract also this adjunction. So the first thing that we have to do is to generalize the construction of this category for an arbitrary tripos, because as you can see, here we have a locality and we can construct this category, but we need to find a construction working for an arbitrary tripos. And for this reason, we observe that in the ordinary case of locale of the sheaf topos for a given locale, well, this category can be presented as the exact completion of the Grothendieck category associated with this tripos. And this category now has a suitable shape for being generalized to an arbitrary tripos. And what we will prove is that, well, for a particular class of triposes that we call, and we will see the definition later, exist sheaf tripos, we can abstract this adjunction in this way, and moreover, we will show that this adjunction here can be obtained by an adjunction here from two triposes, where this one is obtained as the existential condition of this tripos. So, we will show that for all these kind of triposes, we can start with a tripos, applying the tripos-to-topos, and this topos can be presented as the topos of sheaves for a certain Liouville triangle topology, which depends on this, which is obtained by this adjunction. And this situation generalizes exactly the ordinary Sheafification for the locality case. As corollary of another result that I will present in the final part of this talk, we will show that every set-based tripos, so for example, the realizability tripos, is an existing shift tripos. So we can present its tripos-to-topos, that is, in this case, the realizability topos, as topos of shifts for a certain logarithmic topology, which is obtained by this adjunction. And this is essentially our main goal for today, explaining this picture and showing that this is a tripos and this is a topos. Before starting with all the detail, here you can find a list with some references where you can find the main tools that we use to prove our results. So here there are the two papers regarding the tripos-to-topos construction. Here there is a paper by Manny about the characterization of Lex categories whose exact completion is a topos. And here there is these papers about doctrines and tripos-to-topos for different settings. For example, here there is an analysis of this construction for the case of elementary and existential doctrines and so on. So here you can find the main tools that we will use today. Now I want to quickly introduce some standard definitions and fixing the notation for the rest of this talk. So I will say that a functor from a category with finite limits into the category of if semilattice is a full primary doctrine. So this is a simple generalization of the original notion of hyperdoctrine. Here I'm using this particular instance of the notion of primary doctrine introduced by Maietti and Rosolini. And well, a full primary morphism of doctrines is given by a pair where the first component is a functor preserving finite limits, and the second component is a natural transformation from the doctrine, from the full primary doctrine P, into this functor obtained by composing this doctrine with this factor. Now, we will say that full primary doctrine is full existential if for every arrow of the base, this functor, so I'm using this notation to denote the evaluation of the functor on this arrow, well, this functor has a left adjoint, and this satisfies the Beck-Chevalier condition and forbids reciprocity. I don't want to give all the detail, but at least I will just recall, for example, that the Beck-Chevalier condition is a condition that says that the existential quantifier commutes properly with a field substitution. And well, if we have two full existential doctrines, we can define a morphism of full existential doctrine, and this is precisely a full primary morphism of doctrines, such that for every arrow of the base of C, we have that this natural transformation commutes properly with the existential quantifier. Okay. Now I want to quickly recall other two notions, because this is essentially the crucial notion that I will use today. But before, I want at least to recall the definition of hyperdoctrine. Again, since I'm assuming for today that the base category has finite limit, I will speak about full hyperdoctrine. And well, a full existential doctrine is said a full hyperdoctrine if for every object of the base, this poset is an eighting algebra, and for every arrow, this functor is a morphism of eighting algebras. Moreover, we require that for every arrow of the base, this functor has a right adjoint, and this satisfies the Beck-Chevalier condition. So this is an instance of the original notion of hyperdoctrine introduced by Loria. A full hyperdoctrine is said to be a full tripos if for every object of the base there exists another object that I denoted in this way in the base of the base, and a membership predicate, an element of this fiber, such that for every element of an arbitrary fiber of this form, well, there exists an arrow from y to this object such that alpha can be written in this way. So a tripos is essentially a higher order version of natural doctrine, and now we will see some complete examples of triposes and natural doctrines. Well, if we start with a locale, we can define a full tripos in this way. We can take the representable functor, sending a given set into the poset whose elements are functions from this set into the locale with the usual pointwise order. And this is a full tripos. Another relevant example is the so-called realizability tripos. In this case, we have to start with a partial combinatorial algebra, PCA, and we can consider a functor sending a given set into a partial order set defined in this way. We have that this is the set of functions from this set into the power set of the PCA, and then given two elements of this set, we will say that alpha is less or equal of beta if there exists an element, a weakness of the PCA, such that for an element of x, we have that this, and all element of this set, we have that this is a well-defined element, and it is an element of this set given by applying beta to x. Now another example of full tripos. Well, let's start with a category with finite limits. We can define a full existential doctrine, which is called weak subobject doctrines or doctrine of variations. And this is essentially given by the functor that takes a given object of the base, and well, this is defined as the positive reflection of this slice category. This in general is just a full existential doctrine. This functor, the weak subobject doctrine, is a full tripos precisely when the base category has weak dependent products and a generic proof. Now, I said at the beginning that the first thing that we have to do in order to generalize the ordinary Sheafification is to define, is to generalize the construction of the tripos-to-topos for a given locale to an arbitrary tripos. And well, here is our generalization. So we can start with a full tripos, and we will, well, before I need to recall what is the Grothendieck category of a tripos, and then we will see the definition. And well, we will say that we will call this category the Grothendieck category, and well, this is given by the objects are pairs, where the first component is an object of the base, and the second is an object of this fiber. And the morphism of this Grothendieck category associated with this tripos is given by an arrow of the base such that this holds. Using this category, we can then define the category of P preshifts for a given full tripos. So we start with a full tripos, and we can define this category, the category of P preshifts, as the exact completion of this category, of the Grothendieck category of this tripos. This is a Lex category, so we can apply the exact completion. And this is our generalization of the construction of the preshift topos for a given locale. Notice that we will see this in the following slides. This category in general is not a topos, it is just an exact category. We will see later what are the conditions that we need for this to be a topos. And well, as I said, this is a proper generalization of the ordinary construction of the topos of preshifts, since, well, if we start with a locale and we consider the locale tripos, then we have this equivalence. So the preshift category is equivalent to the exact completion of the coproduct completion of the locale, but again, this is precisely the exact completion of the Grothendieck category associated with this tripos. In the case of the realizability tripos, we have that this category is very close to be the category of assemblies, but it is bigger. So again, we have that also in this case we can define a suitable category playing the role of category of pre-sheaves for reusability tripos. Now, we have seen how we can generalize the construction of the category of pre-sheaves. Now I need to introduce the two constructions that are involved in our results, which are the tripos-to-topos construction and another construction that is called full existential completion that freely adds left adjoints along all the morphism of the base of a given tripos. Here you can find all the detail. This, as I said at the beginning, is a construction that takes a tripos and produces a topos. I don't want to recall all this construction in detail. Here you can find all the references, but I want just to recall that this, if we start with a tripos, this construction produces a topos. And the second construction is what we call the full existential completion. Again, here you can find all the detail, but I want just to recall what is the idea. Well, this construction is a construction that takes a full primary doctrine and produces a new doctrine, denoted in this way, which is fully existential. So, this doctrine has left adjoints along all the morphisms of the base category. Some examples of triposes arising as a full existential completion. We have that the realizability tripos for a given PCA is an instance of the full existential completion. The locality tripos is an instance of the full existential completion if and only if the locale is super coherent, and the weak subobject doctrine is always a full existential completion. So these are three examples of doctrines arising in this way. Now, an interesting property of triposes, or more generally doctrines arising as instances of this construction, is that, well, if a doctrine, if we consider a full tripos, and this full tripos is an instance of the full existential completion, so there exists a full primary doctrine such that when we apply the full existential completion, we obtain our tripos. Then we have that the tripos-to-topos construction of this tripos can be presented in this way. So it is the exact completion of the Grothendieck category associated with this primary doctrine. Again, some examples of categories obtained by combining the tripos-to-topos construction with the full existential completion. Every reusability topos can be presented in this way. We have that every topos of pre-sheaves for a given locale can be presented by combining these two constructions. The topos of sheaves for a given locale can be obtained in this way if and only if the locale is super coherent. And finally, the exact completion of Lex category. Now, our definition of exist shift tripos. Now, let us consider a full tripos. We will say that this full tripos is an exist shift tripos if the Grothendieck category has weak dependent products and a generic proof. What we have is that the following for a given full tripos, the following four conditions are equivalent. Well, we have the first one says that P is an exist shift tripos. The second one says that the weak subobject doctrine on the Grothendieck category of this tripos is a full tripos. The full existential completion of this full tripos is again a full tripos. And finally, that this category, so the category of pre-sheaves for this doctrine, is a topos. So, under this, if we have this condition, then our category of pre-sheaves, in particular for our full tripos, is a topos. And then, if we start with a an exists shift tripos, we can prove that there is an adjunction of triposes where this is our tripos and this is at the full existential completion of this tripos. That is again a tripos because this is assumed to be an exist shift tripos, such that this composition is identity. And of course, this induces an adjunction of toposes here, such that this composition is again the identity. So this is a geometric embedding in some sense. And well, we can. The crucial point is that if we want to lift this adjunction of triposes to an adjunction of toposes, well, it is really crucial that these two functors are triposes, because in general this morphism is just a morphism of full primary doctrine. So in general, if for example these two are just hyperdoctrines, we cannot lift this adjunction of hyperdoctrines to an adjunction of their exact category. So it is really crucial here to have two triposes. And you can find an analysis of this fact in this paper by Frey. As a corollary, we have that for every exist shift tripos, there exists a Lorentzian topology on the tripos-to-topos of the full existential completion of this tripos, such that the tripos-to-topos construction of this is equivalent to the topos of shifts for this Lorentzian topology of this topos. Now, we have seen the definition of exist shift tripos, but well, in some concrete cases, it is quite hard to check if a given tripos is an exist shift tripos, because we need to check the Grothendieck, we need to show that the Grothendieck category of this tripos, for example, has a generic proof, and this is really hard, because in the Grothendieck category there are two different structures which are mixed, the structure of the base category and the structure from the fibers. So in order to find more examples of shift triposes, we provide in this result some sufficient conditions which are simple to check. And as we can see, under this condition, if we have a full tripos satisfying these three conditions, then this tripos can be proved to be an exist shift tripos. And the three conditions are the following. The base category as weak dependent product. So you will see that here there is just the base category and not the Grothendieck. So the structure of the fibers is not involved in this condition. And similarly, we require that the weak predicate classifier has a power object in the base category, and that the base category admits a suitable factorization system such that every AP of this class splits. Under these three conditions, then this is a shift tripos. As a corollary of this result, we obtain that every full tripos whose base category is the category of set, assuming the axiom of choice, is an exist shift tripos. And then we can obtain, this is the last slide with the examples, and then we can obtain as a corollary of our result the ordinary Sheafification between in the locality case, but also we can prove that this Sheafification can be generalized in the case of realizability triposes, because this is of course a set-based tripos, so this is an exist shift tripos, and then we have that every realizability topos can be presented as topos of shifts for this Lorentzian topology of this topos. And with this example I can conclude, so thank you very much for listening.
Any questions or comments?
You kept saying things were full tripos systems. So what does the full mean?
It is just to stress the fact that the base category has finite limit, because in general, in the general definition of tripos, for example, as defined by Pitts, the base category has just finite products. So here I'm using this notation just to recall that we work with triposes whose base category has finite limits.
I just want a clarification. So what are you calling a generic proof?
A generic proof in the sense of, for example, you can
The
find...
definition of existing triples, for example.
What
are you calling a generic proof? What are you referring to as a generic proof?
It is essentially you can find this, for example, you can find this for this generic, okay, this definition.
Next slide.
Okay, you can find this notion, for example, in the works by Manning, and it essentially says that the weak subobject up to it is a full tripos. So this is the reason why we need to require this generic proof. This is just a requirement that essentially is useful is necessary and sufficient to add that this is a tripos if the category has also weak independent products. But you can find all the definition in the works, for example, by Manning.
Question that occurred to me, in the world of realizability toposes, there is the notion of ordered PCA that was introduced, I think, by Hofstra and
Yeah.
Every ordinary unordered PCA embeds in the ordered PCA of its finite subsets.
Yeah.
And this gives you a relation between two realizability toposes, which is very like the construct that you're done.
Yes.
Is that
Yes.
a special case of it?
For example, in the works by Hofstra, he used a monad that essentially plays the role of the full existential completion in this case. So it is an instance of this construction for set-based triposes. So yes, of course, there is a connection.
At some point you mentioned a paper by Fry, a couple of slides.
Yeah.
Which one is it?
It is, this one. It is essentially, because as I said,
By Fry. I heard Fry. Okay.
No,
Thank
Fry.
you. Thank you.
Any more questions?
I'm really sorry, this isn't a question that I had, but could I hear more about this example if you take a PCA and then you do subsets of that PCA? Maybe.
We can discuss that over coffee. So I think we should close this session now and thank you.